Hi, my name is Danilo, and in this presentation I will talk about the work developed at Wrocław University of Science and Technology. The title of my presentation is Anatomical and Structural Changes of Anterior Eye with Age, and it corresponds to the third project of the European network AGEYE, which is a Marie Curie initial training network action to foster research training in vision sciences. I will start this presentation talking about the anatomy and structure of the anterior eye and how it may be influenced by aging. Then, I will move to the work developed in Wrocław. In the first instance, we developed a new methodology to infer the corneal structure based on OCT speckle. Using this methodology, it was possible to study the corneal aging, swelling, and intraocular pressure. In addition to this methodology, we used anterior eye surface data to estimate with high precision the corneal scleral limbus and the scleral radius. Then I will talk about a new procedure to perform ray tracing using Chebyshev polynomials. Finally, I will end up this presentation talking about the main scientific goals achieved with this project. This image here corresponds to the anterior eye, where we have the sclera, the cornea, anterior chamber, and posterior chamber, where we have the crystalline lens. So, as you can see, cornea is the first layer that rays find when coming into our eye. It is responsible for about 2/3 of the total optical power. Cornea is an avascular tissue organized in 6 layers, where stroma constitutes around 90% of the total thickness, being responsible for the main optical and biomechanical properties of the cornea. Looking into stroma using confocal microscopy, it is possible to see that there is a change on the concentration of keratocell density from anterior to the posterior stroma. This change varies around 15% between healthy subjects. In addition to this natural variation, changes in corneal stroma occur with aging. The most significant changes happen at the level of keratocyte cell density and collagen fibrils. Studies have shown that there is a decrease of the keratocyte cell density with aging and an increase of the collagen cross-linking due to the accumulation of glycation end products. Given the importance of the corneal properties in many different applications, such as applanation tonometry and contact lens fitting, we decided to develop a new methodology to infer the corneal structure. In this methodology, we assume that backscattering in OCT images is produced by local heterogeneities in refractive index. Therefore, tissue cannot be modeled as homogeneous medium characterized simply by a scattering coefficient, but instead must be considered as optically heterogeneous composite of microstructural segments with different dimensions and refractive indices. The first step of this methodology is to do the proper corneal layer segmentation. Then, a region of interest must be selected. The following step is to apply proper signal processing techniques in order to improve the signal-to-noise ratio. Then, the best model to fit the corneal speckle must be chosen. The parameters can be estimated using the maximum likelihood estimator, and the final decision can be based on model selection criteria, such as the AGEYE key information criteria. Finally, the parameters of the chosen model are used to study the changes in the corneal properties. Based on this methodology, we performed 3 major studies. In the first one, we studied the effects of aging on corneal structure. For that, we collected and analyzed the data of 65 subjects aged between 24 and 73 years. In the second study, we analyzed the role of corneal swelling on cornea, using the data of 4 subjects. Lastly, we studied the effects of intraocular pressure on cornea, using for that a new data set of 56 subjects aged between 22 and 78 years. Here we have an example of 4 OCT images of different subjects with different age. Looking only to the morphology of the image is pretty difficult to point any difference among subjects. The only thing that we can see is that there is a change on corneal thickness between subjects. However, there are cases, as shown here, where we have subjects with the same thickness but with different age. Then, taking account all aging effects that occur in cornea, we should expect differences on corneal microstructure. But so far, there is no gold standard to analyze this internal structure of the cornea in vivo. However, when we model the speckle using the generalized gamma distribution, it is possible to observe significant changes among different age groups. These changes indicate us that the tissue is more compressed with aging, probably due to the cross-linking that happens with age. We also observed significant changes of the generalized gamma parameters after to induce corneal swelling. These changes point to a dispersion of the scaters in the tissue, which is in agreement with what we would expect to see after to induce swelling. For more details about the effects of aging and swelling on corneal speckle, please have a look on this open access paper published in Biomedical Optics Express. The last study using corneal speckle was focused on the role of macro and microstructure on applanation tonometry. Tonometry is widely used as the main screening tool supporting glaucoma diagnosis. Still, its accuracy could be improved if full knowledge about the variation of the corneal biomechanical properties was available. Therefore, we studied the macrostructure using the central corneal thickness, the corneal radius, anterior chamber depth, axial length, and wide-to-wide corneal diameter. The microstructure was studied looking into the speckle statistics. Lastly, aging, which affects the macro and the microstructure, was also taken account. Considering the macrostructure, central corneal thickness was the only parameter which presented a significant correlation with the non-corrected intraocular pressure. These results are in agreement with the studies shown in literature. Regarding the microstructure, a significant correlation was observed for age and all parameters of generalized gamma distribution when compared to the non-corrected IOP. After to correct the intraocular pressure using CCT, age dropped its significance. However, the generalized gamma parameters remained significant. These results, which were recently submitted for a publication, showed us that aging is not a linear process. In fact, studies have shown that just 10% of aging is by a natural process. Another topic of this project included the study of the anatomical features of the anterior eye. Regarding this topic, we started by developing two new methodologies to estimate the corneal scleral limbus. The first one was based on the minimization of the mean square error using the approximation by Zernike polynomials. The second one took into account information from the grayscale image. Both methods were compared with a parametric approach to estimate the limbus based on image intensity and with a manual demarcation procedure. The results showed that precise topographical limbus demarcation is possible either from the frontal digital images of the eye or from the 3D topographical information of corneal scleral region. However, the results demonstrated that the corneal scleral limbus estimated from the anterior eye topography does not always correspond to that obtained through image-only based techniques. For more details about this work, please have a look on the paper published in AGEYE Transactions on Biomedical Engineering. Based on anterior eye topography, we also developed a new and precise methodology to measure the scleral radius. In this method, we started by acquiring the data using the profilometer, eye surface profiler. Then, the position of the limbus is obtained using one of the methods mentioned previously. Based on that, and considering that limbus is rather a transition zone, it is necessary to remove circular bands around limbus. In addition, we also removed the outer bands, since this information may not necessarily correspond to the scleral topography. Then, We added the position of the axial length to the model, acquired with IOL master. Finally, a spherical approximation based on least squares is done, allowing to obtain the scleral radius. Here is shown the final result of the spherical approximation based on the anterior eye surface data. The results show that three-dimensional topography acquired with the eye surface profiler, together with the given estimate of the axial length, can be used to calculate the scleral radius with high precision. For more details about this work, please have a look on the paper published in Contact Lens and Anterior Eye journal. During this project, we also had the opportunity to develop a new ray tracing algorithm. Ray tracing is a powerful technique to understand the light behavior through an optical system such as the human eye. In this method, a two-dimensional ray tracing procedure for an arbitrary number of surfaces and arbitrary surface shapes has been developed, where surfaces, rays, and refractive indices are all represented in functional forms, being approximated by Chebyshev polynomials. The Leeuwen-Brennan eye model has been adapted and used for evaluating the method. Further, real measurements of the anterior corneal surface of a normal, astigmatic, and a keratoconic eyes were substituted for the first surface in the model. The results have shown that performing ray tracing utilizing the two-dimensional Chebyshev function approximation is possible for non-circularly symmetric models, and that such calculation can be performed with a newly created Chebfund toolbox. For more details about this work, please have a look on the paper published in Applied Optics. In summary, the main scientific contributions of the work developed are as follows. A new method to access the corneal microstructure based on statistical modeling of OCT speckle, detailed analysis of the influence of corneal macro and microstructural parameters on applanation tonometry, a new procedure for measuring the scleral radius combining the topographical data and biometrical data, and two new methodologies for estimating the corneoscleral limbus based on anterior eye topography. Other scientific contributions of the project include contribution to the principles of operation, accuracy, and precision of an eye surface profiler, and a new simplified numerical ray tracing for two-dimensional, non-circularly symmetrical models of the human eye based on Chebyshev polynomial approximation. Finally, in this slide is shown the list of publications. Basically, the work developed in Wrocław University of Science and Technology was disseminated through 7 scientific journals and presented in 8 peer-reviewed international conferences in the field of biomedical engineering, ophthalmology, and optometry. Thank you for watching the video and feel free to contact me at any time. Finally, I would like to mention that this project has received funding from the European Union's 7th Framework Programme under the Marie Curie Initial Training Network AGEYE, Grant Agreement number 608049.